Okay guys, that camera just turned off on me, so this is kind of a quick part two to the little presentation I'm doing. I was saying, I don't know exactly when I got cut off, so let me just back up for a second. T is linear just means that the zero vector must go to the zero vector. If that's not true, then T is not linear. Okay? So this is a good example of that. I can tell you that if I input this polynomial, ax squared plus bx plus c, and associate this output matrix with it, it's not going to be linear. Because if I look at what T of 0 is, I do not get the 0 matrix out of that. So therefore T is not linear. You don't have to talk about whether T respects addition or scalar multiplication here. It's just automatically a quick no in this case. All right, so that's one thing you can do. Now, if I had changed the problem slightly, let's suppose I'm going to make things a little more interesting. If I change this one to a 0 also, right, just one little change, right, then we could come back and ask the same question here. Is this linear now? We're still inputting a quadratic polynomial. We're still outputting a 2 by 2 matrix. But this time, if you check T of 0 this time, you do get 0, 0, 0, 0. So that does check out correctly. Just because it checks out does not mean, of course, that T is linear. That's just a first level of check. You still, in this case, have to check that T respects addition, and 2, that T respects scalar multiplication. Let me just show you the respecting multiplication part this time. I think I did the addition part on another one. Let me just check the multiplication for you. Okay, so this time what you're going to do is you're going to take a constant times ax squared plus bx plus c. Okay? Now if you take a look at that, the first thing you have to do, algebraically, is multiply the k into the polynomial, right? The scalar multiplication comes first. This transformation happens second. The first part, though, is to just multiply this through. So ka x squared plus kbx plus kc. Right. Okay. And now my coefficients here are ka, kb, and kc. Right? So I've run out of room. Let me come up here to continue. What is T of this guy? Well, here's my formula. Let me just put a box around this. It's clear. Here's my formula, right? So I need to output 0 here and 0 here. This says 2 times A. But what we really mean is 2 times whatever is in front of x squared. So in this case, that would be 2ka. Right. And what about the lower right corner? B minus c. Well, that really just means the x coefficient minus the constant coefficient. So that would be kb minus kc. Okay? What you'll notice here, guys, is that you can actually pull out the factor of k. Right? If you pull out the k, look what you get. Right? You have the k on the outside, and you're left with just what T of ax squared plus bx plus c is supposed to be. T does respect scalar multiplication. Okay? Turns out that T also respects addition, and I would encourage you to try that part. For that one, you're going to, of course, have to use 2 polynomials, ax squared plus bx plus c, and then you're going to have to add that to dx squared plus ex plus f. Right? The variable is always x, but you have 2 different sets of coefficients for those 2 polynomials. Okay? So that's how that would work. Okay, so this matrix does work as an output to a linear transformation. Turns out that this does work if I put 0 and 0 here. But as soon as I have an entry in this matrix that's not 0, it's like got a number associated with it other than 0, you usually have some problem, right? It's usually going to be a problem. Okay, I'm going to show you one last thing. I know you've been patiently watching this here. I really hope this is helping. This will get the material to you faster. And the faster we get it down, the better, I think. So I'm just trying to help that to happen. So one last example. Okay. One last example here. This is a little bit of a different nature. Okay. You might wonder, like, what's so great about having a linear transformation as opposed to just any old function between two vector spaces? Why is it that when t respects addition and scalar multiplication that we think that is a good thing, right? So I'm going to give you an example to show you how this can be a powerful, useful thing. Suppose that I know that t is a linear transformation. Let's suppose t goes from R2 to P2 of R. So I'm inputting sort of two numbers here, and I'm going to output a quadratic polynomial, basically. Okay? And let's suppose that that is linear. Let's say we know that it's linear. I didn't give you the formula yet, but I know that it's linear. Right? And let's suppose that we know a couple of things. So if we know that t of 1, 0 is equal to 3x squared minus 5, and t of 0, 1 is equal to 7x plus 2. By the way, even though there is not an x squared term here, this polynomial still belongs to P2 of R, because P2 of R consists of polynomials of degree 2 or less, right? Let's suppose that we know these two values already, and we know that t is linear. So I have not given you the formula for t, but I claim that based on this information alone, we can find the formula. This is really powerful. It means if I know what my transformation does just to these two basis vectors, then I can find out what t does to any other point a, b. Right? Here's the reason. Here's the reason. See, if I want to know what t of ab is, do you agree that inside of those parentheses, I can take AB and think of it as A times 1, 0 plus B times 0, 1? I mean, look what you have inside the parentheses. This is just A0 plus 0B, which is just AB. I'm just basically busting it apart again, right? You know, the whole bust out the variables thing. That's basically what I did right there. Now, in this calculation here, you have both a scalar multiplication and an addition, a plus sign in the middle of that. T respects both of those things. So you actually can totally bust this thing apart. You can pull the A out and evaluate it times t of 1, 0. And then plus, you can pull the B out of the second part, t of 0, 1. Right? So this is a combination of t respecting addition and t respecting scalar multiplication. Right? So now, look what that means you can do. Right? This means we have A times whatever 1, 0 transformed to, 3x squared minus 5, and B is multiplied by t of 0, 1, which is 7x plus 2, and I can simplify that as 3a x squared plus 7bx, right? And then plus negative 5a plus 2b, which is a constant term. There's the formula. It's really amazing. If I just tell you t of two specific points in the xy plane, I can calculate t of any other arbitrary point. So if I want to know, for example, what is t of 10, 10? Well, I just put in 10 for A and 10 for B in this formula, right? I'll get 30x squared plus 70x minus, let's see, it's, 50, and so it's negative 50 plus 20 would be minus 30. There you go. That's t of 10, 10. You can find t of any point A, B that you want by just using this formula. So that is one of the powerful things about linear transformations, is that if you know how a small set of vectors gets transformed, you can figure out how all of the rest of the whole vector space gets transformed. Okay, that's it. That's the main things I wanted to go over with you. Thank you very much for your extra time on this. Hope you're having a good weekend. If there's any questions about any of this or about the homework or whatever, feel free to come in. My review packet is posted, so I have extra office hours this weekend. I'm going to be doing a review session on Sunday evening. Of course, if you can make it to that, that'd be super. Just let me know how things are going. I really want you guys to get this stuff and to appreciate it and do well. So, all right, that's it for tonight. Thanks so much.